Hello everyone, my name is Eraj Khatiwada and today I'll be presenting my project titled Enhancing Tensile Testing Images Using Fast Fourier Transform for CNN Training. This project is part of my coursework for ISAT 6900 under the guidance of Dr. Yoshida and Dr. Coleman. Tensile testing is a critical method used to evaluate the mechanical properties of materials such as their strength and ductility. During this test, a sample is pulled until it breaks, revealing valuable insights for industries like manufacturing, material science, and engineering. High-resolution images are captured throughout the process, showing key features like crack propagation and material deformation. However, these images often suffer from noise and low feature visibility, making it difficult for machine learning models, especially convolutional neural network or CNN, to effectively learn from them. CNN is a specialized type of deep learning algorithm mainly designed for tasks for object recognition, including image classification, detection, and segmentation. My objective in this project is to use fast Fourier transform or FFT to pre-process these images, removing noise and improving feature clarity to enhance CNN training outcomes. Here you can see the original tensile testing dataset showcasing the three tensile testing phases: elastic, plastic, and fracture. Each phase presents unique deformation characteristics, but also suffers from noise and low visibility, as shown in these images. To address these issues, we applied a 2D FFT to a sample image from the plastic phase. As shown in the graph, we can see the frequency and its magnitude after FFT. Since half of the data in the Fourier transform is identical, I've used the second half in the second graph to provide more clarity and detail. This process allowed us to visualize the frequency component and identify the noise-dominated DC component, which is located here. My advisor suggested we remove the DC component first. After removing this DC component and performing an inverse FFT, we would reconstruct the image. This pre-processing step was designed to enhance clarity before training the CNN model. If this method improved accuracy of the model, we plan to further refine the dataset by targeting high-frequency noise components for removal. Before we applied FFT pre-processing, a CNN model was trained using the original tensile testing dataset. The model struggled to learn from the noisy images, which resulted in a low accuracy of just 55.55%. This shows the challenges of training a CNN with noisy, low visibility images. The next step was to apply FFT pre-processing to see if we could improve the model's performance by enhancing the image quality. Accuracy in machine learning refers to correct predictions divided by all predictions by the model, and it also shows overall performance of the model. The table shown here is called confusion matrix. It is used in machine learning to visually evaluate the performance of a classification model by comparing its predicted classifications against the actual known classifications. Just by looking at this table, you can tell how good a machine learning model is. In this presentation, after training a new model, I have shown the confusion matrix of the model so that you can know how good a model is by looking at it at a glance. We decided to do FFT-based pre-processing in two parts. In part 1, we applied FFT, removed the DC component to reduce noise, reconstructed the image using inverse FFT, and trained the CNN model. In part 2, we went further by also removing the highest frequency component and its conjugate pair to suppress finer noise. The images were then reconstructed and used for training. Here is the code and technique that was used to remove the DC component. I'm using Python and libraries like SciPy to apply 2D FFT. Here I'm reading all the images in grayscale and then 2D FFT is applied, and then the frequency domain was modified by removing the DC component and setting it to 0. And then we apply inverse FFT to reconstruct the image and save the image to the output folder. This algorithm was applied to all tensile testing images. To verify if the previous code worked, we are comparing the original spectrum versus after removing DC component in one of the sample images. In the original spectrum, you could see there is a tall bar, which is the DC component. Notice the DC component is set to 0. And you could see the magnitude axis, y-axis got reduced. You can see the difference here in the range. This versus this. And this shows that the removal of DC component worked as intended. The new tensile testing dataset was ready after removing DC component using FFT for all the tensile testing images. Here we can see the original and FFT processed images for each phase, elastic, plastic, and fracture. Notice there is an improvement in clarity and feature visibility for each of these phases. You can see the image looks much better, and the patterns, the tensile testing patterns, are more vivid here. These enhancements make it easier for the CNN model to learn key material features. After training the CNN model with FFT process dataset, we observed an accuracy increase to 61.11%. This marked a significant improvement over the original dataset's accuracy of 55.55%. The confusion matrix of this model is shown here. Since part 1 of the pre-processing technique improved the accuracy of the model, we continued to do the part 2. In part 2, we took pre-processing a step further by removing not just the DC component, but also the highest frequency component and its conjugate pair. Highest frequency noise can obscure finer details in the images, so removing it aimed to further enhance clarity. The images were then reconstructed using inverse FFT and used for CNN training. This is the code snippet that was used on all tensile testing dataset, and the final dataset was prepared. To verify if the previous code worked, we are showing Fourier transform spectrum after removing DC component versus Fourier transform spectrum after removing DC and highest frequency component. If you see on the left, the range of the magnitude is more than the magnitude on the right. And if you see over here, this graph has DC component removed along with the highest frequency component, but this one only has the DC component removed, which was the part 1, and this is the part 2 of our image processing technique. And you can see over here, we successfully removed the DC and highest frequency component, which can also be made sure by checking the magnitude spectrum in this graph. You can see the step-by-step transformation from the original image to the final processed version after removing the DC and the highest frequency component based on magnitude. The final image looks clear and of less noise than the original image. This algorithm was applied to all tensile testing images, and the final dataset was ready. Training the CNN model with this final dataset resulted in an accuracy of 66.66% compared to the original accuracy of 55.55%. This demonstrates the impact of FFT-based preprocessing on model performance. In conclusion, removing the DC component using FFT reduced noise and significantly improved CNN accuracy. Further suppressing high-frequency components enhanced image clarity, aiding in better feature extraction. Overall, FFT-based pre-processing proved to be a powerful tool for transforming noisy tensile testing images into a robust dataset for CNN training. This approach highlights the potential of FFT in optimizing machine learning applications for real-world data. These are the references that are used for this project. Thank you for listening to my presentation.